Einstein described a situation to Leon Rosenfeld in 1933. He should have said, because of conservation of linear momentum, history would have gone a totally different direction if he'd said that right then. But he didn't. We will obviously be able to deduce the momentum of the other particle. We will deduce the momentum. Same with position. We measure the position, it's symmetric. The other one is symmetrically on the other side of the original. Therefore, we know where it is. Yeah. If he'd said knowledge at a distance, Carlos, if he'd said knowledge at a distance, the reason these two are found to be exactly opposite, even though they are both randomly found, up or down, is because of the conservation of total angular momentum. It's because there's a cause coming from their original preparation, which stays true because we can't allow the total angular momentum to be other than zero. Okay. And it's true at all times, no matter what they're doing. Not that we know what they're doing, not that we know they're in any particular place or in any particular spin, but that they are always opposite to one another. That's my work.
In quantum mechanics, it gets very fuzzy in terms of, we're talking about observation, the observer versus a conscious observer versus a measurement versus, say, some disturbance in the system that causes, say, a collapse of the wave function.
Wonderful questions. Wonderful questions.
Can you help me understand what is required? Because as far as I can tell, consciousness is not required, but I don't know if that's, I think that's true. That's what I can tell from my understanding of things, but different people, different interpretations. Is that accurate?
That's a wonderful question. Let's say where and why and how consciousness is important and necessary in physics, and how it is not at all required for the universe to go about making its own decisions. Quote, I can anthropomorphize the universe. How is it about to do that? It doesn't take conscious observers to get us to where we are. Pacha, Donald Hoffman, and his idea that we need consciousness before we get the world.
Bob Doyle is an astrophysicist who calls himself the information philosopher. He's had a whirlwind career from Brown to Harvard to working with NASA. He's written 4 books and runs the incredible website informationphilosopher.com. Bob, thanks so much for coming on.
Thank you very much for being here, Carlos.
Yeah, it's great being in your space. And Bob's given me a wonderful tour of his home, and we've gone through a lot of the history of your life. But I'd love to jump to perhaps the main focus of this conversation, and how I discovered you was from your wonderful website, informationphilosopher.com. And I actually, I discovered your website, it was 2 summers ago. I was on the roof of my building doing research on different topics, and your site came up, and pretty quickly had 20 tabs open on my Chrome browser, because I was down every rabbit hole you could imagine. And I said, I have to save this site. This is a place I will definitely come back to. And even your books are available on the site for free and as PDFs. And I was going deep into those books as well at the time. And I reached out to you a few weeks ago to chat. We have a lot in common. So I have so many questions to ask you about, different things to cover, and we can kind of navigate and find pockets that we'll both be interested in.
Okay.
But if you wouldn't mind, I mean, for the general audience out there, can you explain what is information and why is it so important?
What is information? Well, it's come into existence in connection with computers. One of the inventors of the earliest digital computers was Claude Shannon, who some say wrote a book on the theory of information. Actually, his title was The Mathematical Theory of Communication. And he said that what's being communicated is information.
Right.
The information in telephones was what he was interested in, because Bell Telephone was interested in a theory of how much information they could send over a wire with least power or bandwidth and so forth. So it had a technical background in telephones and the telephone world, but it turned into the communication of information, which we all recognize today, that we're living in this information age, and that almost everything that we do is somehow information. Our media, our newspapers, our publishing, printing, all of the books that have been written throughout all time are a knowledge base. All of it is information in the general sense of the word information. But information can be, thanks to Shannon, a much more technical definition that allows us to break it down mathematically into quantifiable amounts of information, which he then developed the idea of bits of information we all talk about these days. There came to be called bytes of information, which is a very popular term too, that our websites are made up of bytes and kilobytes and megabytes and so forth. But the idea that information is somehow the best way, in my view, of trying to understand what an object is, a physical object, is to say, what is its information content? And how did that information content come to exist in the object? And a deep question, which we'll get to a lot in this talk, I hope, with you, is which comes first, the object or the information? Because in my view, the universe started in a state that had zero information. That is to say, it was in a maximum state of disorder, of chaos. There was, should you have been alive at the time to have looked at the early universe? First of all, the universe at that time was billions of degrees, and you would have been instantaneously ionized, so you couldn't do any looking.
Sure.
But at least you can imagine what it'd be like to sort of look at this earliest state of everything we know. 13.75 or 13.84, according to the Webb telescope. We're going to nail a few more decimal points. At this earliest moment in time, there was nothing of interest. Nothing that looked any different from anything else. It was just a haze of light, brilliant, higher energy light than we've ever seen, witnessed with our eyes, which would have been burned instantly had we looked. And yet we are here having this information, you and I, this conversation, using information, Carlos, to talk to one another. And when I first came to Harvard in 1958, I had been studying the work of Arthur Stanley Eddington, a guy who looms very large in my work, and in work that he wrote about the nature of the world and how he understood the world and what was going on. So Eddington had raised the question of thermodynamics and what's called the law of entropy, that disorder is like an end state, what the 19th century physicists called a heat death. That the universe might have begun, they thought, in the 19th century, or really even back to Newton. The universe may have began in a certain state, which was, the way the Greeks thought of it, as an early golden age. And since that time, we've been declining all the time. And that the drift of history was going from a wonderful, good origin to a horrible ending. And it was called a heat death, because the universe was going to raise its entropy, and there's no way, according to the second law of thermodynamics, that entropy can do anything except increase. That given nature, entropy always increases. Eddington confronted that thought and said, you know, it seems like a worrisome thought. But he also then said, it's very strange, among all the laws of science, all the laws of physics, most of them have a kind of a symmetrical relationship in time. Laws of gravity, how planets go around stars, they come back to the same state. They keep going and going. All the laws of mechanics that were known at the time, even electricity, which is becoming understood with Maxwell, all these laws have a kind of symmetric state and a kind of a deterministic lawful behavior. And he said, among all the laws of science, there's something very strange about a law which tells us that things are going to get worse. It's a kind of thing that has a value judgment, that things used to be better, that they're getting worse. There's something in this law that he thinks we need to consider it different from other laws. It seems to be, if you had to put it in a category, and you would should I put this entropy law in with other laws of mechanics, like the force creates the acceleration, or every action has a reaction, or all these other laws we know, Newton's laws. This one seems to have more of questions about value, about good versus evil, good versus bad. It seems as if the entropy law is telling us things are going to get worse. And so he set me in a path of thinking. that's gone on to this day. And much of my work today is whether a question in philosophy and in morality and ethics, a question is, are there any objective values? Or are all our values created by our cultures? So we're reading, you and I, Donald Hoffman, who thinks that before the universe existed, there should have been or could have been a consciousness about what the universe would become, because these conscious intelligences throughout the universe would have created the universe we're in. Now, to me, this is a very ancient view of a beneficent, omniscient, omnipotent God who's pre-thought everything that ought to become in his creation and has brought about a creation that is worth having. Well, now we're in the law of entropy, and it's saying, no, everything is winding down, grinding down. It's going nowhere. It's getting worse all the time. So I came to Harvard again, 1958, just studied with this great thinker, Bruce Lindsay, and we read his book with Henry Margenau on the philosophy of physics. And we read Eddington. And so the question becomes, is the universe going to get better or is it going to get worse? And the way I put that question to my professors at Harvard, I'm just a first-year graduate student, I said, we're taught that the universe began in a state of equilibrium, maximum entropy, maximum chaos, disorder everywhere. How, I asked them, are we having this conversation? And
Right.
I'm
Seems like a
asking
paradox.
you of the
Yes.
same question, Carlos.
Yes.
How can we be having this information if entropy can only go up? And I began to see, well, there's another way of looking at entropy, that when the entropy is low, we call it sometimes negative entropy, it contains information structures. And so if the universe began in maximum entropy, there would have been minimal information. So then my question to my professors became, where did all this information come from? How could it be created? Now, to them, I tended to talk in physical terms, not so much information in terms of knowledge, but that became my greater later interest. At how do we know what we know? How can we know more in the future? How does humanity build knowledge and share it and create it and make ourselves all better by educating everyone, whoever they are, and having everyone who's a human being realize they can create things of value for their future, for the next generations? That's been my thought. So how, when I explained or talked about information with my professors, it was information in objects. How did objects form? For example, at the earliest universe, it consisted, according to modern standard theory of particles and so forth, of nothing but quarks and gluons and photons and things we know are now the elementary particles that lead to atoms, that lead to protons, the neutrons that are in the nucleus of an atom. No atom could have existed then. It might have formed for an instant, but it would have been immediately destroyed by the billions and billions of degree temperature. The energy would blow apart anything that tried to become an object. And so I was asking them to help me understand that, and it wasn't clear that they had thought about this problem. And so among all the professors, one stood out to me, and that was my wife's thesis advisor, David Laser, who wrote a wonderful book called Cosmogenesis. And in this book, he too began to look into questions that we shared over the next several years. He and I argued quite a bit about free will, for example. And free will was a topic that was brought up by Arthur Stanley Eddington in his book called The Nature of the Physical World. Because when Eddington first wrote or spoke about his work in a major way, it was the Gifford Lectures that he gave in 1927 in Edinburgh, where these great philosophers and thinkers are asked to summarize their work over a course of a few days of speaking to a scholarly audience in Edinburgh. And when he gave that talk, he said, we have now answered a question which we long wondered about. The question is everything in the universe happening for reasons that are part of the laws of nature? And he said in his lectures, we can now say we know the answer. Yes, the universe is completely deterministic. Everything happening in the universe is happening according to a law. And that law might be a Newton-type law, action and reaction, or force creating acceleration. All of the laws of physics, since they apply to the world as a whole, from the stars, from the galaxies, the cosmos, all the way down to atoms, we will comfortably say everything that happens has happened for a cause which has become an effect. And that effect in turn becomes a cause for the next effect, and so on. And we are nothing but a sequence of causal processes. The universe is entirely caused by something that came from the beginning. Okay? Now, obviously, the Gifford lectures have a background of being lectures about the connection between science and religion, and how the universe formed according to traditional religious theories, that there was a creator. And that this creation that we have here was put in motion, the way Newton put it, that God had created this physical universe, set it in motion. It was following laws that Newton discovered for us. And I think Newton, who was a very deep religious thinker, thought he was actually getting to understanding God and the works of God by finding the laws by which the universe had been set in motion, famously like a clock, and that we are a clockwork.
Right.
The universe is a clockwork, so are we. Everything that happens because it was caused by events that preceded the ones we're in now by a few moments, and that the chain of causal chain controls the physical universe. So we've answered the question. Everything is perfectly determined.
Oh, that's it.
And then came Werner Heisenberg.
Yeah, blew it all up.
Published his book, his article on the uncertainty principle in 1927. It must have been wonderful imagining being in Eddington's position, having just given a lecture saying that hundreds of years of thinking, starting with religions who said an omniscient, omnipotent being had done it all, and that's why we're here, come around to an idea that maybe the universe was all just determined, step after step, no human freedom, we're actually some kind of robot. Imagine picking up an article by Werner Heisenberg who says, at the atomic level, things are happening that cannot be explained by classical physics. Things are happening that cannot be understood by Newtonian mechanics. We need another kind of mechanics, which came to be called quantum mechanics, because the little quanta that are interacting of energy between particles, which are material particles, so we have now a theories of energetic particles, light quanta, we think of them, material particles like electrons and protons. There's a connection between these which introduces a kind of fundamental indeterminism, uncertainty. Well, in the nature of the physical world, you can read how Eddington comes to say, well, maybe this randomness, this freedom, this could be a niche, a crack in the deterministic world which could open the door for human freedom. That began my work in 1950s, we say 57, 58. And when I came to Harvard, I talked it over with David Laser and others, that I think there's something here. I think we should be studying entropy. I think we should be maybe, instead of just writing equations, which astronomers, astrophysicists like me were doing, is how do we calculate the light coming out from the sun? How is it transferred from place to place? I said, shouldn't we looking at things in terms of the entropy that's in this radiation, or the entropy that's in the physical objects, like a star, like a sun, a star, a planet, objects which are on our planet? Shouldn't we think about how much order or information is in them? But where does all this information come from when the second law of thermodynamics says we cannot go from chaos to order? We always go from order to chaos.
Sure.
Okay. So that was setting out my problem for the rest of my life.
Yeah, that's so much
that
to
a
cover. I
good-
have a bunch of questions, bunch of things to ask you about there. Now, the second law of thermodynamics, the reason why we're having this conversation, one of many, is that locally there can be order, right? Things can self-organize. We can have, is that, you're
How
looking,
can they do it if the universe was all around us at an infinite temperature?
Oh, I mean, eventually.
Yeah.
So,
Okay.
yeah, after
So
400,000 years or so,
how do we
right?
get? What is
Yeah.
it? What is it? And this was David Laser's insight. I thought for many years.
Yeah.
How have we been allowed to have a situation where in local areas in the universe we can have pockets? I used to call them of order. An object that
Right.
came into existence, whether that was an atom, and we got the first atoms that could stay existing 380,000 years after the Big Bang. We couldn't even have an atom as an object that would last and have a long life and last until today. The atoms you and I are made of were coming into existence 380,000 years after the Big Bang, and they're here today, and we are us. They are us. Some people like to say, and I like this one, that the atom hydrogen and the atom helium are capable of being created in the Big Bang, but it couldn't create carbon, nitrogen, oxygen, potassium, things you're made of, I'm made of. Where did they get made? It turns out they had to be made at another time after the universe had completely cooled down
Sure.
and some places reheated and formed stars. After the universe cooled down, the sky went completely dark everywhere, and only hundreds, not of thousands, but hundreds of millions of years, it got so expanded and so dark that some objects, which we think of as planets or stars, astronomical objects, came into existence because gravity took over in a certain area and pulled the material together with its universal gravitating force. And some of them were so big and so heavy that as they pulled together, they heated up and they turned on thermonuclear explosions in their interior, which could convert hydrogen to helium. Now, some helium would have been primordial, but in this star, when hydrogen got converted to helium under this enormous pressure going on in our sun, the light coming in our windows, not this LED light on our work today in the studio, but this energy of the center of these stars, the temperature would get so high that the smaller atoms could be combined in fusion to release energy more, and they could create other elements, because when you take two hydrogens and make a helium, energy is given off. That's going to be the future of energy source on Earth, for many, as far as we can tell, in many ways. But then when you take a helium atom and bang a proton into it, you can make a lithium atom, that precious metal today, which is hard to find, precious atom, which is driving our electric cars with lithium-ion batteries.
Sure.
Okay, then lithium could maybe make beryllium, and beryllium could be built up to boron. But it turns out you can't go from lithium to beryllium to boron to carbon by stepping it up. It turns out that the physical reaction rates of such atomic building to the larger atoms in the periodic table does not work, and they're very unstable. So when you create some lithiums, they tend to fall backwards under the fall of more power and being hit by other atoms. And there came a time in 1950s when I was first a graduate student that Fred Hoyle, the great Fred Hoyle, wrote wonderful books about cosmology, had another way of thinking about how the universe existed, which was wrong. He called it a steady state theory, that the universe had always been like this. Totally radical idea that there was no big origin. And he had to fight against those who thought the universe may have had a creation. Remember, in religions, there are some religions, some of our early science was in the form of thinking about how we all came about. Some said, the universe has always been like this. Others said, no, we had to have a creation, and there had to have been a creator. And it turns out that in the long run, those who said the universe was always like this lost to the ones who said, no, there's been a creation, and we found evidence of the creation.
Sure.
Well, that put a lot of energy into certain schools of thought, religions in particular, that we need to explain this creation. And so in a way, early on, I have never been particularly religious, but I grew up Catholic. My mother wanted to send me to a Catholic school. I departed Catholic schools in the 4th grade, done with that, and going to public schools. But in any case, this is another one of my questions is, do we have a creation? Yes. Do we have a creator? Any sign of a creator here? No. There is a creative process, which I think if we understood that creative process, we would give the same sense of reverence towards this process, this thankfulness, this gratitude that we have a wonderful life because a creative process brought this world we're in into existence. But I can't find any conscious being with a mind in view that someone named Carlos Farias someday should come meet Bob Doyle and have a conversation. I can't get there like
Sure.
some others we know
Fine,
have
yeah.
done.
I'm not going to try to force you that way either. It's an open question. Well, can you explain then? Yes. So can you explain the creative process? What are the rules, or what are the dynamics going on there? How do these things relate?
So I have a web page and many supplementary pages called the Cosmic Creation Process.
I've seen that. Yeah.
Creation without a creator. This is quite radical, and I've saved it for my last book, should I live long enough to get to that book, because it will upset a lot of people, I'm afraid. All through my years of thinking about these things, I realized I was kind of getting involved in issues that many people feel are life and death issues. People who attack the idea that there is a God taking care of all of us deserve to die. Right? There are parts of the world where the thoughts I have right now would cause me to be destroyed. So it's okay. There's been that element, and maybe we'll get to that element some more someday. What was your question again about how explain the creation process?
Yeah, the creative process.
Okay.
Yeah.
Okay. Again, since I call myself the information philosopher, it's because I can boil it down to the question: how can we go from a state where there is little or no information to one where there's lots of information? And let's start with the physical universe rather than the ideas in our minds, which also we have to create. I like to think I can create new information, that is to say, new knowledge that I can share with others. When I had students, I loved to tell them about new ideas that others had taught me, and I pass it on, but then some that I had of my own ideas. And that's a wonderful thought that we can do that as human beings. Let's go back to the universe. We've got nothing but atoms. Now, how can those atoms form into an object that is somehow a sum that's more than its parts? That it is somehow richer in information, okay? And I guess gravity is the most wonderful example because when gravity pulls dust together, it turns into a planet, okay, or even into a star that then becomes a generator of energy. Those are all, you can broadly see how the universe just contains random dust, but then some force, some process, I struggled for words for this. I called these processes initially anti-entropic because they were working against the law of thermodynamics. They're working against this. How could they do this? Okay, the answer to how they do it came out of my work and Laser's work, and I'll show you how it came out of Eddington's work. These two are my prior thinkers whose work I've tried to absorb into my own, and sometimes I thought it was mine, and sometimes I reread them and it goes back to them. But anyway, we have to have a situation where we have only a kind of chaos and we want to create something with an information structure in it. Let me touch back on the star for just a moment, because if I see the universe early as finally getting itself to create atoms everywhere, we now have the material universe, we know it. We could never live and see the quarks themselves because they combine and become something tamed down to our temperature. But when the period of time, which was the earliest stars forming, and they compressed together and heated up to temperatures which never got back to the Big Bang temperatures, but they got back to temperatures 5,000 degrees on their surface. You don't look at the sun with your eyes because your eyes would be burned by the sun. Inside they're 20 billion degrees. And we are talking about thermonuclear fusion, like the hydrogen bomb, going on inside the sun and producing this energy that comes out to us. Now, two things. The energy coming out to us is at 5,000 degrees. We couldn't live in a 5,000 degree world. So what we need is for a star to be located far enough away from us that by the time the light gets to us, it's cooled down to something of the order of 300 degrees absolute, or 0 degrees or Celsius that we live in today, okay? So imagine that the energy coming from the sun has, from the sun's point of view, it's totally chaotic and in equilibrium with the sun. But when it gets here, that energy is expanded and cooled down. And so now we have a low temperature situation. And when you have a high temperature situation in one place and a low temperature situation in another place, that gives you the ability to create what's called a heat engine, a steam engine, for example. If you have a hot place, you can take that energy and use it to push on a piston toward the cold place and create engines. Okay, the whole theory of thermodynamics was an attempt to understand engines, and the idea of entropy came about with the fact that once you've used up the heat, it's gone. You can't get it back again, and so forth. Now I've gotten off the track a little bit. Let me just add one thing right here. When the star in its center creates helium, to make the jump from helium through lithium, beryllium, boron to carbon, and then nitrogen, and the things that are our body, stuff we're made of. Fred Hoyle in the 50s and some other physicists came up with the idea of what he called the triple alpha process. Okay, was famous in my day. You don't hear much about it today. Alpha is the name that the early students of particle physics gave to the helium nucleus. There, in the early days of particles, there were electrons, there were protons. Eventually they found neutrons. We knew all the atoms, but how could we get from pure electrons, protons to a hydrogen atom? And how could we get from 2 hydrogen atoms to helium and then add another hydrogen to get to lithium? So we're building up the elements 1, 2, 3, 4 in the periodic table. Fred Hoyle said maybe the energy in the center of a star could get so hot that 3 of these helium nuclei, and mind you, the star has started with pure hydrogen because the universe was thought to be pure atoms, which were hydrogen atoms, not anything larger except a few helium. Inside the star, you would have formed helium. Now, once you have lots of helium and it's still up this billions of degrees, what if 3 helium atoms collided with one another, 2, 2, and 2, and glued into a 6 and made a carbon with a jump from helium to carbon? He would explain all the rest of them because it turns out later calculations show you can move from carbon to nitrogen. And you cannot make this jump. And so the triple alpha process of Fred Hoyle got us the whole creation of the chemical composition of the universe and all of the elements and the chemical composition of human beings. Do you know that we are more like the universe composition than a lot of other places like the Earth itself? There's some interesting stories there.
Sure.
Anyway, let's go back to your
reminds me, I think
questions.
you were going to touch on the Neil deGrasse Tyson,
Oh, I know.
mere stardust.
Yeah.
Oh, yeah,
Now,
sure.
so the issue is the universe began, material universe, with a lot of dust particles, really just hydrogen atoms and a few helium.
Sure.
But now, when they were burned up in the center of the sun to give a star to give off energy, they built the heavier elements, and those heavy elements get distributed to the rest of the universe when stars explode, the big heavy stars, the supernovae and all of this. And those become what we call second generation stars that have a large amount of heavy elements. Well, that includes not only second generation stars, it now includes the planet like Earth, which is made out of all those heavier elements. But the heavy elements couldn't come into existence except in the center of stars. So in a way, we're all made out of stars that died for us. It wasn't Jesus that died for us. It was a star that died for you and me. And it distributed dust. So in a way, we're all stardust. That's been a popular line.
Yeah,
I've
Neil
noticed.
deGrasse Tyson. Yeah, a lot of people
right.
remix that. Okay, so one thing that'd be helpful for me to know, when does information begin? When's the earliest information that you think existed?
When is the first information object?
Sure.
When is a physical object capable to hold itself together so we can see it, getting around to the relationship between our observing and the universe? What is the relationship between the universe, which has no observers, which has creation without a creator? What is going on in the early universe? And by that I mean up to around several billion years before things like you and human living things can come about. Okay, so let's see. The question is, give me the question again.
When does information begin?
When does information begin? So in some sense, the information in the early universe, we quantify it by its temperature, its density. Maybe if we knew the exact chemical composition, what portion is quarks, what portion is electrons, what portion is proton. There are no protons yet for 380,000 years. Number of photons. We say we have this number of photons, this number of that. That's the chemical composition of the early universe. That's information. But notice how little it is to describe this vast universe. We have nothing specific about anything interesting in particular here or there. The whole place is smooth, even. And here's something that practically nobody who kind of works on cosmology understands. The universe did not begin at a point and expand away from a point. Because the best theories of cosmology, in my opinion, and I'd like to write more about this, but others are way ahead of me on it, is that the universe was always infinite. It could not have, if it had a point, if it formed at a point, and it expanded for 13 billion years, 13.84 now, or whatever, what would be outside it?
Nothing, right?
Nothing.
A lot of people would say that.
Well, now, what is nothing? Is space nothing? Is space a void with nothing in it? These are questions that are very deep around the issue of what is space, what is time, how do we understand them, and so forth. So it turns out that the universe as we see it, as far as we can see, it is always about the same as we look back in time. And the Webb telescope right now is allowing us to look farther back in time than we've ever looked before. It seems as if the universe continues on indefinitely. Now, there's the ancient question of whether the universe, whether the solar system had a center and other places that were not the center. And the famous work of Galileo and Copernicus to come around to this idea that maybe there wasn't a center to the universe, that at least our sun was not the center. It is the center of our solar system, which led us to believe that there's a center and here we are on the edges and so forth. Right. Instead, our view of the universe now is anywhere in the universe you put yourself, or imagine yourself to be in earlier times, looking around would see the universe expanding away from it, all the other galaxies expanding away from it. And now we come up with what's called some called it a perfect cosmological principle, some called it a strong cosmological principle, and it's beyond the idea that the laws of physics are the same wherever you are. This is the cosmological principle, sort of astrophysics basis, that the laws of physics are always the same wherever you were in the universe. You cannot distinguish where you are in the universe, because everywhere will have looked the same. They will all look to be the center of what's going on. Everyone's leaving me in all directions. I look out, I see, no, what's happening here? All the galaxies are disappearing.
Losing stars at the horizon, right?
Right.
Yeah.
So these are deep kind of cosmology questions and just human, how do we fit in the universe, where are we in the universe questions. But coming back to the exact question, where did information really start? There was, as I look back, if I could imagine myself in the universe at that early time and at 10 billions of degrees, there were quarks flying by and maybe I could have seen them, but today it's hard enough to see an electron in an atom because the position of the electron, as Heisenberg pointed out, we're uncertain about where it is. Sure. We can only say probably where we're going to find it, when we find it. And we calculate probabilities where we find electrons with quantum mechanical theories, sure. which are amazing theories, and they make predictions. They don't tell us facts. They make predictions of what the fact might turn out to be when we make a measurement. And in a sense, depending on what we choose to measure, we bring into existence that measurement. For example, if you try to measure the spin of an electron, it's not obvious, or quantum mechanics says it does not have a spin until you measure it and find that it has a spin. This leads into the question of how much observers or conscious events in quantum mechanics bring about
sure.
these questions that you know about. So coming back to information, there would have been information, but it was in a state of chaos. There would have been particles that could have been live as something different. A quark, two quarks could have gotten together and made a meson, or three made a proton and a neutron, and then they could join with an electron, and they might have done in that early universe, but then they would have evaporated, right? Until these years later. And so now we're on to probably the core of my work now, based on Laser's work, David Laser's work, and Arthur Stanley Eddings' work. What is it that got us away from this incredible state of chaos into the state of order that we're in today, that allows us to think and know things and see the world? And the answer is the expansion of the universe.
Sure.
The expansion is the driving force. The expansion of the universe opens up spaces between the particles, which now give you, if you don't maybe know much say about thermodynamics, but the way we talk about thermodynamics today is what's called statistical mechanics, in which we actually do the math of individual particles, where they are. And when you jam lots of them together in a space, there's a limited amount of what we call phase space. If you've heard of phase space, it's the product of the position space that we ordinarily think of as space, and then the momentum space, the momentum of all the particles. And what we need to do is put particles into what are called phase space cells. And what the great Ludwig Boltzmann, who is the creator of statistical mechanics, showed us and developed a whole theory of statistical physics and mechanics, is that we can explain a gas of molecules or particles by telling us where every particle is, that's its position, and how fast it's moving, that's its velocity or its momentum. And that these are then distributed in phase space according to probabilistic laws. Boltzmann then introduced probability before quantum mechanics discovered that physics is probabilistic and statistical. So Boltzmann is one of my great thinkers in the history of the development of science and so forth. And then Einstein came along to completely rederive all of Boltzmann's work, all the math, himself in 1902, without having really known it had already been done by another great statistical physicist named Willard Gibbs, a rare American in the history of physics. He was at Yale, and he also did the math that led to our work on entropy and so forth. But now, I don't know if I've really nailed your answer, or where does information...
Yeah, well, I think, one thing actually, to even take a step back from that, when we're using the term information, when you primarily use it, are you referring to like Shannon's information, or is it different type of information?
Very, very closely related.
Yeah.
If you, say you were asked, you were charged with explaining exactly what's going on inside that pen that you're moving right now. What is this pen object? If we got down to it, the deepest we could go, searching for the truth, the real bottom line, what's here. And the answer would be we could digitize it, we could quantize it. We could say there are, let's see, I guess maybe 10 to the 30th atoms, and they're all this atom and that atom. We've got some carbon in the plastic I see there. We've got some aluminum in there, and we can say where the aluminum is, and we say where the carbon is, and we can say they're all oriented in this way, and it's arranged, and someone put it together in a wonderful system, and it's doing something. But at the level of information, we can just say at the level of bits of information what exactly is where. Connect and how it is connected to everything else. It starts to look like what I call an information object. It can be described by information. And why do we want to do that? Because today we have tools like our computers that have developed the ability to create three-dimensional representations in motion, which simulate things in the physical world. And to me, that is our very best tool for teaching, which unfortunately today I don't teach except my books and my website, but basically making a 3D animation. You're now making these interviews with great illustrations and mostly two-dimensional things, but we can make three-dimensional things which visualize, simulate, and demonstrate the physical world. That is the ultimate teaching tool that I think information philosophy would lead to, because we'd say, if I can make a three-dimensional animation which you can watch work, you would be closer to the truth.
Oh, for sure. Absolutely. I'm 100% with you on that. That's why I think visuals, like I think I may have spoken with you about on our last call, I like to throw visuals at people.
Yes.
That help explain, even if it's not perfect, even if it's just analogous to
you're going to get them closer by.
It's closer, yeah, and far more people can, grok can understand something if it's presented in some kind of moving image
And not words.
And not words, or a combination of the two. You can speak over a visual and explain it and help, but even further into that, though, to add on to what you're saying. If you have a structure you can play with, you can touch, you can feel, tactile, that you can interact with, and it pushes back on you. That is really...
We can make physical models of what we're imagining going on at the small world or the bigger world. Yes, models are good. And for a long time I thought what I was doing was trying to imagine building models. And many scientists, I think all the time in terms of a model of how they think the world is working at the moment, whether it's the interior of a planet or a star, what's happening in our sun, for example, what's the chemical combination, all the helium in the middle, and then you don't see it near the edges and so forth. Those are models. But are doing it in computers, and computer animation is wonderful because anyone can do it. We can all take part in this, creating a knowledge base of the world in the form of animations that will teach you or show you what we think is happening in reality.
Yeah. It's amazing. So that actually clears up a lot for me, because when I think of, say, Shannon entropy, Shannon information, it's a little bit different than what you're talking about.
It is.
Because as far as I understand, Shannon information, that requires a sender and a receiver, right? That requires a channel, that requires...
As I said, Shannon's
something
book,
to communicate. It's more about communication than it is about how colloquially we would use information.
Correct.
But average person,
absolutely
doesn't think about it that way.
Right. So in the way, remember, Shannon's book is widely thought to be the theory of information. He did not think of it as a theory of information. The title is A Mathematical Theory of Communication. So he created the information in the form of bits to describe how much we could stick into a given channel.
Sure.
All right.
Got it. Perfect. And then you just touched on, this is something that, the difference between, in quantum mechanics, it gets very fuzzy in terms of, we're talking about observation, the observer versus a conscious observer versus a measurement, versus, say, some disturbance in the system that causes, say, a collapse of the wave function.
Wonderful questions. Wonderful questions.
Can you help me
disturbance?
understand what is required? Because as far as I can tell, consciousness is not required, but I don't know if I think that's true. That's what I can tell from my understanding of things, but different people have different interpretations. Is that accurate?
That's a wonderful question. Let's say where and why and how consciousness is important and necessary in physics, and how it is not at all required for the universe to go about making its own decisions. Quote, I can anthropomorphize the universe. How is it about to do that? It doesn't take conscious observers to get us to where we are. Pacha, Donald Hoffman, and his idea that we need consciousness before we get the world. So let's break that apart a little bit.
Sure.
Quantum mechanics is a wonderful subject. I have spent 60 years teaching it, reading about it, reading everybody who are worried about quantum mechanics. And there's a lot of people who just are not happy with it because it remains controversial, right? It's what is the interpretation of quantum mechanics? What can we get from, how do we understand what's going on? So I would like to be able to teach some of that, and I have in mind a book on the quantum. But it's a very long story, so let me try to back off a little bit and see where consciousness is involved. When Heisenberg said when you make a measurement, you have to be looking at the thing you're measuring. Let's say it's an electron. And he created the notion of an X-ray or a gamma ray high particle microscope with light coming in, and we could figure out where the particle is. And Heisenberg's thinking is worth holding on to because it's sort of the beginning of an observer looking at a physical object that's in the quantum world, okay? So I've got some diagrams on this on my web pages, but imagine that we're looking into the microscope and visible light, we can send invisible light. It turns out we can't see at that microscopic level as easily as sending in more energetic light because if you light waves are long. A typical light wave is microns, angstroms, depending on what your units, 10 to the minus 8th of an object of like our size, of a meter. We're talking about going down 8 orders of magnitude to get to the size of the object we're looking at. Now, if we use light to look at it, we've got this wave, and what comes back is a wave, and we have this big fuzzy nothing. Right? So what Heisenberg said is we have to use shorter and shorter waves because when the wave is coming in, it's going to bounce off and come out. We need to have some small waves so we can measure it accurately. But the smaller waves, the smaller a wave is of light, the more energetic it is. And the more energetic it is, the more it slams into the particle and sends it off to we don't know where. So in this microscope experiment, he said we see why there's uncertainty. Because if we try to see it more closely, we just push it away from where it was. We get an error in the position. Not only that, if it was sitting still when we hit it, it now has a different velocity, a different momentum. We get errors in the momentum and the position, and that's the uncertainty principle, that the product of the error in momentum P and the error in position X, the delta P, delta X, must be around H, or Planck's constant. That's all. You can visualize it, Carlos, and if someone is ever going to make a good visualization of this for people in the future, I've never seen one, it would be, you should maybe see Heisenberg looking at the problem. And it has to do with a disturbance, he said, as you said, the word disturbance, because when matter is disturbed, it has another value, and we may not know where it goes. There's uncertainty about where it goes. It's okay. So the Heisenberg microscope experiment deserves a bit more teaching.
I agree. So what is the rule? If you had to describe this rule or dynamic, this process, is there some kind of exchange here between energy and information? I mean, as say, the energy, you see what I'm trying to talk about here is sort of like, is there an exchange? Does information require something physical?
Yeah, let's sort of, a couple of thoughts about how to describe it. Let's focus on another big question, which will be another book, okay? Yeah. But it's going to come down to information and how it interacts with energy and matter. Okay. This book will be, and my website is made up and it has these drop-down menus. So there's a drop-down on freedom, there's one on values, which will be one of my books.
Oh, right, yeah.
There's one on
mind, life.
Mind, of course. Now the one on life is trying to explore the beginning of those objects, which the universe had objects before it had living objects, okay, what was that transition? When did information stop being a property of objects into something that one object was sending to another object? What was that all about? Now, this is a way of looking at the origin of life, and there's a wonderful group at Harvard that meets on the origin of life. And they all worry and think about the chemistry, the earliest elements in a pond somewhere that's kind of a scum that somehow manages to get together and turn into a living thing, and it's been quite vague for a long time. So
right?
I feel that if you were home in on that problem of the first living thing with information in mind, Carlos, we would have another way of seeing what it was that was happening, all right? Okay, so let me...
Okay, I ask a quick question.
Sure,
Is there no
please.
information exchange before living things, inanimate objects, inanimate atoms, let's say? Is there not information being exchanged between them?
Not information that's going to be usable or used. There is definitely information of a sort.
Yeah.
First, the sun is shining down on us. We have information that there's a star there. That's information. It's coming from the sun to the earth. I look in my telescope and I can see planets. I look in the web and I can see galaxies that are back near the origin of the universe. That's information traveling in the universe. But let's get to the break point, the difference between information that's being exchanged between information using information objects. Information objects that are going to use information for something. Okay? And this is a little complicated, but this is a nice little story. I don't think I've written it this way, so I'm going to try it because you're looking for an explanation.
Yeah, that's great.
All right, so let's imagine this. Let's start with the fact that at some point, in some place, notably on the surface of the earth or maybe in a deep thermal vent in the bottom of the oceans, where we had an energy source in the form of magma breaking up, ultimately volcanoes, but hot vents coming into the lowest part of the cold ocean. How did ocean get there? How did water get there? There's a wonderful story. But here we are, here comes this heat. And now there are molecules, more and more complex molecules. People in the complexity theory group, the Santa Fe Institute people, they think it's all about a story about complexity. And the more complexity, the complexity will eventually become adaptive. We'll have complex adaptive systems. It's a wonderful whole world of jargon and talk about explaining things. I think of Stuart Kaufman. He and I have exchanged a lot on this. He loves all this stuff. But I would like instead to say, complexity is like saying, life is complex. Yes, it is. Complexity is a worthwhile concept, but it isn't explanatory. You just can't say, okay, it became complex. So let's focus now on replication. Suppose a molecule got to be quite long and complicated, and somehow these components of that molecule were wandering around, and somehow they got to line up with the molecules in the original, and it accidentally found that it could make a replica of itself, that one molecule could become two. Okay, given that as a premise, we have everything we need to do all of life and all of evolution, because it is nothing but a combination of replicating faithfully, but not perfectly. I don't know if you know, but there's some biologists who say if replication had always been perfect, we would never have anything but that original molecule. We would just, it always could only do one thing. It needed accidents. And now we're into a deep philosophical area, which I'll get you to ask me about later. How is chance and randomness playing a role in the creation process? Because it takes a combination of chance and adequate determined processes. Let's come back to the replication. You write that down.
I'll go for it,
Okay. The replication can form other similar objects. Now, how do we get from replicating molecules, like DNA eventually, to things like a cell, because the life seems to be a time when a wonderful object forms which has a boundary between itself and the environment. And that boundary seems to be something like a little thin film bubble,
membrane,
which we can create these right now by putting oil in water. So basically, the Earth is a system that has a lot of water, and it needs explaining, because there was a time when there wasn't any water.
Sure.
We were in it wasn't an oxygenating environment. It was, previously a different type of environment. But I could go so many ways with this. I'm in trouble. What's your question again? What's the origin of information? Are we still on that, or origin of life?
We're getting in there. Origin of life. We're
Let's
getting
stay
into.
origin
I was
of life.
asking what the rule is, the dynamic.
What's the rule?
Yeah,
Okay,
if you had to break it down, I think.
Right.
Yeah.
Yeah, it's not like a rule, but a
set of
bunch,
rules.
a
Maybe
few
it's a
rules,
set of rules.
just a
Yeah,
few
maybe,
rules.
yeah,
Let's
yeah.
stay with that. So let's say rule one is molecules have come to be able to duplicate themselves, replicate themselves. Okay, second rule, though, they don't always do exactly the same thing because there are accidents. Chance comes into the world. And now we get some molecules that are different from the others. Now, what if some of the different ones coming along find a way to replicate themselves much faster? Okay, better. Now, we have the basis for what Donald Hoffman likes to think, that life, what it's all about, evolution, is trying to get things that are more fit to reproduce themselves. His way of putting it is to say, it's all about having more children. We need sex, we need children. But we take it all back to my story near the beginning. We have molecules, and they're replicating, but some replicate better than others. We can say they have more reproductive success, which is a technical term for what Don Hoffman says
Fitness,
is
yeah.
have more kids.
Yeah, fitness.
Okay.
Yeah, we could say.
Yeah.
Yeah.
Okay. So now we're on the verge of getting, I think, to much closer to where we are now. Imagine, I guess I've got to take the leap into the cell for a moment,
Sure.
because there's more we could talk about there. Imagine now that we have cells, and the cell contains a lot of chemistry inside, and it has this distinction between itself and other cells. And if we take cells we know today that were primordial, the earliest ones, bacteria, single-cell organisms, sometimes eukaryotic ones came along, but the ones that are prokaryotic are not the source in the tree of life where we come out. Even the prokaryotes have a life. These are the earliest cells are living things. They can duplicate themselves as a whole. How do they do that? Well, a couple of ways. They break in half, and the two halves go their ways, and they become complete after one another. We have to have that in our story before we get to information going between objects, and which objects make use of the information. So imagine now you're a little bacterium, and maybe if you're in a liquid environment, you have a little tail on you, and you wiggle this way and that way, okay? Now, it turns out, I have a great friend now in the form of one of Werner Heisenberg's sons. He had quite a few sons. One of them was named Martin, and in sometime in recent years, he wrote a Nature article explaining that fruit flies are going and doing things at random. And they are, this randomness is a critical part, and it might be thought of as something like free will. It could be. That even fruit flies have an element of free will. So I wrote a letter to Nature. My first publication was in Nature.
Wow.
Just starting with a publication there.
That's a good place to
And
start.
I said, in the letter, basically it's short, it's just half a page in Nature, but it says Martin Heisenberg thinks that this randomness could be an element of freedom, just like Eddington had said, right, to me many years earlier. So I wrote to Nature saying, I have a model, there is a model of free will, which today people think of it as my own model, the two-stage model. But once I formulated it, I started discovering other people had written about things that I see, I recognize as my thinking. So I now am giving credit to earlier and earlier people. Okay, I take it back, in my first book, I took it back to William James, because William James said chance has to be involved here. And we can go into the details of that, but I'm way off the story of life when I do that.
That's okay.
But anyway, take me back. Let's
Martin
now go back to
Heisenberg?
this. Let's go back to a cell. If you ever and or fruit fly, in Martin Heisenberg's work. Martin wrote back to me and said, "Oh, Bob, thank you very much for connecting me to William James. I can't imagine anyone more important, just wonderful thinker. And I don't know that I understand at that level. Great thing." And we went to conferences and other things. So let's get back to the little bacterium, which is a perfect example of what Martin Heisenberg wanted to see in the smallest animals. The bacterium is sailing along, and it has on its surface receptors. All cells have receptors today. Some are T receptors, and we get viruses through them, all of that. Along the surface of the bacterium, these different sensors have different things they can sense. Information they can sense, okay? So now we're getting to information in a living thing. And for example, it might sense the temperature. And it might detect a temperature gradient along the bacterium. Or it might detect chemicals. And some chemicals may be food, others may be toxic. So now we have this bacterium, as he moves along, there are these gradients of temperature, gradients of food. So you could say, I'd like warmer, I'd rather be warmer, or I'd rather get food, or I'd rather avoid toxins. These things are harming me. And now we have a little element of a being that has a kind of will and a purpose and a way of getting to where it wants to be via chance. Because what does the bacterium have? Only two modes of motion, okay? It can only do two things. It has I've drawn illustrations of this, you'll do better ones. Out of the back of the bacterium come these long, they have names.
Flagellum?
Flagella, thank you. There are two of them hanging out of the back, and they can either rotate, say clockwise or counterclockwise. And they are such that, and there is, by the way, a 3,000, 5,000 RPM motor inside the cell. That's as fast as any normal electric motor we build today. And it's working purely at the biological level. And I've written about that and tried to understand it as much as I can. Anyway, when the motor goes this way, the flagella wrap around one another such as to make a beautiful, like it's a beard that has been, put together. So, and the bacterium goes forward only. Goes forward, goes forward, goes forward, until it stops and the motor goes the other way. When the motor goes clockwise instead of counterclockwise, the flagella separate, and they're independent, and they're random. And the little bacterium just rotates randomly until it stops, and the motor goes the other way. So you have two things it can do. Go in this direction, sense the direction, and then decide to stop or not. And let's think about its choices. Oh, this is warmer. Let's keep going. Oh, that looks like food. Let's keep going. Or, wait a minute, that's toxic. Let's stop. And what does he do then? He goes the other way and he tumbles. And what does that do? Give him a new direction to try. And there is my model of free will in a bacterium.
So how do we know that it's, how should I say this? I'm not,
Where are you going with this question? Yeah,
it's like I play devil's advocate here, but
yes, good.
How do we know it's freely making the choice, right? It has the agency, right? How do we separate that from just being an automatic behavior?
Oh, sure, okay.
Yeah.
Let's take there's automatic behavior. That leans back to the people, the determinists, who say it's only doing what it's doing because it evolved to do that. It has no idea what it's doing. I agree, it doesn't have any idea what it's doing. When I call it a choice, it's because I'm modeling a two-stage model of a random element which generates possibilities. Those possibilities then need to be chosen between, and they may be chosen at random, or when we get up to higher animals, they may be chosen because of something else, which is a complex of experiences that this animal, because I think we are limiting here to animals, that this animal has had in its past, where it's had these choices before, going down that road, that road, that road, and it has a collection of experiences. And when it has the experience it's in, it may say, this is not one of the ones I was doing well in. Now it has a memory, it has knowledge, it has a capability to say, let's look at the other possibilities and let's take another one. Now you're all the way up to my animal version of free will.
Sure.
It has to have experiences which are in fact past causes, so to speak. They become things to do. They're not real yet. They're just possibilities, like quantum possibilities. It's not quantum mechanics, though. It's just experiences that the organism has had that it could now decide to choose between for what to do next. Now, normally, some people say, clearly it will always do the best thing all the time. The determinist philosophers say, no, there's no freedom in this. It's going to do the best thing.
Sounds like an economist.
And that's about how much economists themselves understand economics. Yes, because the point is it also could do something stupid instead.
Which
Some people
people
say, oh,
mostly
God
do.
damn it, I'm out of here.
People mostly do.
Right.
Not rational at all.
Exactly. Rationality is the idea to get to reality. No, we don't use it all the time. There you are. You've got a whole bunch of my thinking buried into those few thoughts.
I do. And that brings us into the experience recorder and reproducer, right?
Yes, exactly.
Which is...
And you know who that is? Donald Hebb.
Oh, Hebb, which you had mentioned
And
earlier.
You really, it'd be nice to go to that because the idea of how, now remember, Crick said we're a bundle of neurons. Okay, how can that bundle of neurons be the basis for my free will model? Okay, and the answer goes through Donald Hebb. Let me just tell you then Donald Hebb right off, okay?
Yeah, sure.
What Donald Hebb said was quite an interesting, wonderful insight. First, we imagine the cortex, which is his expertise, as huge numbers of neurons, which have a base and have a long axon.
Excellent.
And then the base and the axon are connected by dendrites. And the typical dendrites, maybe 10,000 of them on a very long one, are connecting to 10,000 other cells. So the cells are massively interconnected, and every one of them is, I talked to biologists at Harvard in my early days to say whether I've got the right insight into this, and one of them said, I wish I could remember his name and give him credit at this point, it's Bob, the cortex grows in at random. Everything is connected to everything else. Now would you write the phrase, everything is connected? Because you'd like to come back to that.
Yep.
The idea that everything is connected is behind quantum entanglement, claiming that every particle in the universe is entangled with every other particle, and therefore God figured it all out. That's where they, anyway, let's come back to the Donald Hebb.
Hebb, sure.
He said, what happens, he thinks, this is his it's called an assembly of neurons, assembly of cells. So cell assembly was his term. This cell assembly is such that when sensory inputs come into the brain, 1/3 of the cortex is devoted to the visual, and another to the olfactory, and another one to touch, and so forth. So they're all kind of connected into the mass of randomness. So this fellow at Harvard, come on, Bob, get that back. He said, it all grows in at random. The cerebellum particularly is just a phenomenally loaded with possibilities of connections. So what Hebb said is maybe what happens is when a cell fires, because it gets a signal and it sends it out, maybe the path it takes through the mass, and using different words, I should look at my own writing, the path it takes causes the synaptic connections between dendrites and the next axon or whatever, cell body, maybe the path it takes causes it to wire this neuron to that neuron. It causes it to take that possible synapse and strengthen it. The technical jargon is involved with synapses strengthening and what is it called? Something potentiation, long-term potentiation in the work of Eric, what's his name? Long-term potentiation, we'll look up Eric, come on, begins with an H. No, anyway.
Eric Hoel? No.
Who?
Hoel? Eric Hoel?
How are you spelling that?
H-O-E-L.
No.
Sorry, if you said Eric H, that's the guy I think about.
We'll come back to Eric in a moment.
Yeah.
Absolute great
Long-term.
Nobel Prize winner in neuroscience and everything. His books right up there. See those books on the cell? And he's not in the cell, but anyway, let's come back to Donald Hebb. Donald? Maybe let's see, how does he put it? Neurons that fire together.
Wire together.
They wire together.
Yeah.
Okay. That's Donald Hebb. The guy at Harvard said, it turns out that the neurons that don't fire decay, or what he described are cut away. The cortex we have is the one that was never used. The cortex that's left, when it's pruned, he may have used that word.
Pruning, yeah.
When it's cut away, what's left is a record of our experiences, in my words. Sorry, you're hitting the microphone.
That's okay. Yeah, I'll take that out after. Not funny neurons.
Okay.
Okay.
So basically, Hebb says neurons that fire together are wired together. So then it came to me, and I said, well, listen, what if another experience now comes to what I call the experience recorder and reproducer, and it comes in through our visual cortex, a smell. It comes in. What does it do? It pushes into the cortex, which is now selectively pruned away to be what it is now. It comes in, and what if it resembles another earlier experience? Well, then it probably lands on the visual cortex or comes in along the olfactory with certain chemical combinations that match ones it's seen before. And so I take Hebb and I say, he says neurons that fire together or wire together. What if neurons that are fired will refire the original? Neurons that are wired together now will fire again together when any experience comes in, that if you could see this vision that I have, that I don't think anybody talks about this world yet. So Carlos, I'm having a hard time finding words for it. But basically, imagine we are a sensory surface, and we're trying to get into the insides of what we are. And what comes in is a pattern. That would be something acceptable. The pattern is such and such. Suppose it's a pattern we've had before. Come back to the bacterium. I've had that chemical experience before, and it didn't work out well. Even that bacterium can record experiences, okay, at an extremely minimal level. Come back up to our brain now, so we're making a gigantic leap. Now, what will happen when, in my view, when a new experience comes in that we've had before, it sends its stuff, everything that ever got wired together. Well, what got wired in with that original experience? And what's his name? Stuart Kaufman and I, his wife came up to me, or talked to me and said, That's amazing. That you got it or something. She seemed more enthusiastic than Stuart was at what I was saying. But the example I gave in this talk, I was actually online, so she didn't come up to me. She just said hello, kind of thing, or comment at that talk. She was in University of somewhere or other. Come back to that. My example was, imagine that the first experience that a young lamb, say, or sheep had was a yellow and black striped object coming into view, and the next thing you know, its mother had been killed and eaten. Suppose that was a lamb of an experience of a lamb. I said, what do you think that lamb, as now a fully grown animal, might have felt at that moment? And what if the neurons that were getting wired together, according to Donald Hebb, included the hippocampus, the regions of the emotions, and it was frightened to death. And it's burned in because those neurons that are our emotions and our feelings of pleasure and pain were all burned in, so that the next time it sees yellow and black stripes coming, the whole thing happens again, and immediately we have now a kind of purpose. Among the things we can do now, we build on our prior experience. We have knowledge that was not good. And that's already the basis for how choices are made in my model of free will, and how the experience recorder gives us the knowledge base that allow us to freely, and I say freely because we have possibilities much of the time about where we're going to go with our next action as we are agents. Okay, so she liked that one about the lamb being eaten. And I came up with that one on the spot as far as I can remember in that meeting.
That's a good analogy to make. So I would love to know too so we have information objects that are sending information between each other.
Well, they're all in a way, each of these information objects, if we come to bacteria or environments, there are information flows of all kinds in every environment. There are information flows. I mean, the air is blowing, so you can feel the air blowing. You're getting information about air coming at you. So information is flowing in the sense that objects are flowing and moving around. There's a lot of motion. Whether it's an information signal that you should take cognizance of, recognize because you've experienced it before, fresh air, I'm going for it, right? Oh, cinnamon buns cooking, I'm going for that. It's all simple in my model that stuff's coming in, and there are information objects which have learned to sense that information, recognize it, and then based on their past experiences, take actions based on what were the best earlier outcomes and avoid the worst outcomes.
Gotcha.
I don't know where your question just went.
No, that's helping codify some of this stuff. I'm trying to think about if you can, because where this conversation, the last section sort of started was with this leap to living organisms,
Yes.
right? Is there an underlying process? I'm trying to think of, you've heard like universal Darwinism, the idea that things like natural selection, variation, that it goes beyond biology, that there is something, say, more fundamental, say in physics. There's Darwinism, kind of a law that doesn't just start with bio.
I see universal Darwinism.
Yeah, it's like even goes below that. So I'm trying to think, are you saying like a new kind of rule emerges with biology, or is it the continuation of, say, a process, and then biology, and then living organisms are just one other thing? Or is there a real step difference?
See if I can answer the question with this one simple idea.
Sure.
The notion of agents with purpose enters the universe with the emergence of living things. It did not exist beforehand. Everything that happened before, some say Darwinism is not purposeful, but we may think of it and describe it as it.
Right.
But definitely nothing purposeful was happening before organisms evolved, which were able to recognize, sense the universe and other organisms, other living things, and they could mutually decide. They could
Right.
act and interact and communicate with one another. The communications between a star and the Earth, it's not communication, right? Because it's not informing. It's there. It's information to be observed and used. We now study the stars, even though we can't talk to them and they can't talk to us. We get information from them, but it's a kind of physical, non-living information. You know what I mean? It's like you and I are doing something that stars don't do.
Yeah, interesting.
See what I mean? It's
Well,
just-
I guess I don't understand it well enough. I guess
Yeah.
partly in that.
it's hard to use the right words. You know, Hoffman says
Right.
we don't have the right language for this. I like that when he says that.
Yeah.
You know, my slogan is beyond language, beyond language and logic,
Yeah.
because there's nothing logical about physics. We use logic as a tool to reason about physics.
Right.
There's nothing logical happening in physics, because already logic is reasoning, and reasoning is something we do.
Yeah.
Okay, no universal something before living things
Yeah.
was thinking
Sure.
or being purposeful. There were no agents unless there was a God. You can't say that's impossible. It seems
Right.
very unlikely. Knowing how many atoms are involved to get you together and the earth together and the universe together, it's just like trying to imagine an agent in charge.
Sure.
It's so hard. It's hard to write a computer program, never mind program the universe.
Right.
Okay.
So, viewing the world during the universe through this information lens, I'm going to take this a very different place. I mean, there's
good.
I have like
That's
a lot of
good.
different pockets that I want to kind of touch on.
Good.
One would be, does viewing things in this light with the information framework, does this help, would you say, resolve some questions in quantum mechanics? Does this help resolve any other? No, it doesn't. Okay. It doesn't have it.
I think it's.
Is there a usefulness to it?
No. It's, well, you know, I have actually tried to explain quantum entanglement, which is considered to be one of the great amazing things going on. The universe can't possibly be doing this
Right.
because things would have to move faster than light.
Right.
You know the story, Einstein says,
Spooky
I
action.
measure this and that changes. I'm explaining that with information, but no one else is doing that.
That seems like a big deal. Like, can you go into that more? I mean,
If you want, we can
Yeah, please.
send off. Okay.
yeah.
Okay.
That's
It's
a big
just,
one.
yeah.
That's a theory.
That's definitely off in an odd direction. So I have written a page called Entanglement under my quantum drop-down menu, which I refer you to later. And I'm thinking about a book on entanglement, which I hate to keep adding books. Holly says, stop adding books, write the ones you've already got to work on. But in any case, you tell me what you think Einstein found, or Bell and Bell experiments. You've read some of all this stuff about? Okay, what do you think is
little
happening
bit.
with two particles when you measure one and the other one has exactly the opposite?
Right. So, as far as I can understand, when you measure the spin, let's say
Yes.
of an electron over here, or a particle, let's
Right.
say,
It's up or down, it's
yeah,
plus
it's up or down, and you can have them at opposite ends of the universe.
So they say.
So they say, yeah, we can't test
I'll
that.
talk to you about the universe.
But it's,
later.
you can get them as far apart as
You have to-
farther
you
apart
have
than
to-
light
You have
travels.
to send them apart.
You have
Yes.
to send them apart, right?
Farther. Okay.
That if you measure the spin, say if you've entangled them before, you measure the spin for one of them, the up, down will be
Alice and Bob.
Alice and Bob. The other one will be down.
Yeah.
And you can do this. This has been tested many times. It's
Right.
as clear as we know to be objective truth, right? It's close to that dynamic
This
occurs.
is
We don't know why.
experimental fact.
Experimental fact. Yeah, we don't know why, but it seems
Now
to be
Bob
the
Doyle
case,
gives
right?
you an explanation.
Right. And I believe, and we know that they're in a superposition before that, right?
Yes.
That they're not either up or down before that.
Correct.
They're in some combination of the two.
In fact,
Yeah.
if you were just Alice and you did this experiment 1,000 times, you'd find randomly it's up and down. It's random. In fact, let's jump to the quantum mechanics, which adds the puzzle or the problem. Quantum mechanics says it doesn't exist before you measure it.
Right.
Well, if it didn't exist before you measured it, and you got up,
Yeah.
And if his measurement doesn't exist before he measures it, how come he always gets down all the time? Perfect experiment. That's the problem.
Yeah.
Okay? All right. So early on, people had an alternative explanation, which was that somehow, in fact, there are great people I've met with personally, in some cases, have a theory that it was determined. Everything's explained.
Sure.
Right?
Yeah, okay.
End of story. Good physicist, there's no problem. What's the problem? Or it goes like this. Who am I talking about here now? Paul Davies, you know?
I know the name, but I don't know anything about him.
Okay,
I've
wrote
heard
a lot
it.
of books about God and physics. He's a good physicist. Anyway, the idea is, David Laser, by the way, the way he started out, everything happening today was the result of causal chain coming from the Big Bang. Everything.
Yep.
Determined. So therefore, it's pretty simple. Bob's was determined to be down and Alice's was determined to be up. What's the problem?
Yeah.
Okay, so there are people who've shown what the problem is, and I could give you the problem first before you can see my answer to the problem.
Yeah, please do.
So the argument is they have a common cause. Why several things happen in large distances apart? Because they had a common cause. It doesn't require communication between two things. I wish I could give you some good examples. There are people who talk about twins doing the same thing. And you know, it isn't because they doing it instantly. They just had a common cause that came down to this point. So now keep adding to that we don't know these are happening, and they're in a 50-50 superposition of up, down, and down, up. That's the way the Schrodinger equation, which is written to describe the situation, is to say there's a thing called the wave function. And Dirac wrote the wave function with his Bra-Ket notation, so-called. He writes out that and Schrodinger had already described this, which Dirac writes about, that the wave function is a linear combination of up-down plus down-up, or minus down-up in certain, with electrons, plus with photons. This deep physics here. But anyway, it's got up-down plus down-up. Each one of these states could be realized by an experiment. And there's a coefficient on this ket, 1 over the square root of 2, and 1 over the square root of 2 of this one, because when you have a wave function, maybe you've heard this terminology, you square the wave function, and that gives you the probability of finding a particle. So in the case of the spins of the two electrons you're describing, you multiply, you square this one, 1 over the square root of 2 becomes 1/2. We have a 1/2 probability of up-down and a 1/2 probability of down-up, perfectly explaining all of the work in the version of the EPR paradox as built by David Bohm. David Bohm in 1951 wrote a textbook, Quantum Mechanics, and 3 or 4 very important articles, and he said, Einstein's problem was done with just particles in their positions. I'm talking about it in terms of digital electronic states, not digital, but discrete.
Okay.
The problem with particles is they're continuous. Their position can be continuous. But electrons' spins are discrete, up or down. So Bohm said, we're going to be able to measure this much better than the Einstein version of this paradox. So David Bohm, you read my page on David Bohm, has given us the modern version of the EPR paradox, or whatever you want to call it, entanglement, okay?
Sure.
And David Bohm said, the better way to think about this is, imagine you have a hydrogen molecule, which has got 2 hydrogen atoms. They act just like electrons. When they go through a Stern-Gerlach device to measure the magnetic direction of spin up or down, atom is just like an electron. It comes through, and if you set your measuring device, Stern-Gerlach built this thing, send the thing through, there's an inhomogeneous magnetic field which tends, if it's spinning this way, then it goes this way in the field, and if it's spinning that way, it goes this way. You can distinguish up from down. That's the device for telling whether an electron is spinning this way or that way. That's Stern-Gerlach, okay? We don't know what it's going to be when it comes in unless we have measured it and found that it's spin up. comes out, say, this way, okay, it is going to go up or down out of the Stern-Gerlach device. If it comes out up, and you put another Stern-Gerlach device downstream from it, coming out, and it goes through that one, it comes out up again. If you put 10 Stern-Gerlach devices in a row, if it comes out in a spin up, it's said to be in a prepared state of up. It will now go through another detector and still be up, and still be up, and still be up. It seems to have lost its randomness in some way. Now I'm giving you a lot at one time, but you need to hold on to this in order to get the final result out of my entanglement explanation. So people said, most critics who wrote to me, and I have correspondents who write to me, and some have noticed my stuff and say, Bob, you don't know what you're talking about. There's no way the particle has got a state already. But we know that I can measure a spin of an electron and put it in a state. It's a known state. And if I measure it again, it's still in that state. So I'm having this argument with about 2 or 3 people at the moment who don't think what I'm saying is an explanation of entanglement. And others who are finding it, I can't understand what you're talking about, it's getting a little complicated, and they're not quantum physicists. But I think some are coming around to being interested in it. Now let's see. You've heard of conservation laws. Energy is conserved except when it converts it to mass. So now we know there's a mass energy conservation principle. Momentum is conserved. If 2 particles break up and they had certain momentum to begin with, whatever new momentum they have, the total is still the same because they must conserve. Conservation principles grow out of what are called symmetries in the problem. And there's this famous mathematician named Emmy Noether, Noether, who was the first, although it turns out I've now found someone else was involved in this, who saw this right around Newton's time, or amazing early time, named Emily du Châtelet. Do I have her book here? That's not it. Anyway, the notion is that when there's a symmetry going on, unless you break the symmetry, which is a large part of quantum particle physics today, symmetries break and then interesting things happen. Back to the Newtonian physics level, the symmetry of conserving angular momentum is such that, let's take your case, Alice and Bob. Alice measures up, Bob gets down. Total spin angular momentum, 0, right? Up minus down equals 0. When you create the initial entangled particle, the experiment is designed to have total angular momentum 0. So when the particles travel apart, they have total angular momentum 0. Okay, one's up, one's down. They're always opposite one another. Now here's where Bob Doyle comes in. I say, why didn't Einstein realize that the momentum was being conserved? I think he did. I've tried to read his papers to see whether he knew. Let's go back to the simple position problem of EPR paradox. 2 years before EPR, 1935, Einstein meets with one of the great expositors of Bohr quantum theory and uncertainty principle and all that. Einstein meets with a fellow named Rosenfeld. What's his first name? Gosh, it's amazing how my mind sometimes can hang on to things, can't find them. Anyway, Leon. So he meets with Leon Rosenfeld, and he said, let me describe something to you. Suppose I had 2 particles. This is 2 years before EPR. Suppose I had 2 particles and they're coming at one another and they collide and they go off in equal and opposite directions. Now, if I measure this one, I know where the other one is. Do you see why and how he knows? He's applying the conservation of linear momentum. This total momentum is, say, 0, and it is still 0. So if this one is here, the other one must be exactly opposite the original collision on the other side. Why didn't Einstein say, this isn't spooky action at a distance, which he said. Instead, I'm trying to think of the German there for a moment. Fernwirkung was one word, but the spooky had another word. Anyway, he called it action. Why didn't he say, I have knowledge at a distance? I know where the other one is without measuring it. There was no measurement. Instead, and here's a deep thing, and I don't know if you'll be able to hang on to this, but I'm formulating it for myself. Einstein was hung up on these damn Heisenberg, Bohr idiots who are saying things don't have properties until you measure them, and therefore they don't have any properties. He was hung up on that, and he's thinking about quantum mechanics. The other one doesn't have any value. But when I measure this one, I know the value of the other one. How do those guys think? I mean, this is objective reality here, he says to his friends like Max Born in the Born-Einstein letters, if you've ever read those. Oh, very important book. And this is it right here.
Oh, nice.
He's saying, clearly these particles are doing something which don't depend on what we're doing to look at them. There's a reality outside of whether we're looking or not. Do you think the moon isn't there when nobody's looking? Do you think when I look, the moon, he wrote another one to another great physicist at Princeton. Let's see, let me reconstruct this story. He said, and the words he uses to describe the physicists are really funny. He not only idiots, they are woolly-minded. He's got all these wonderful adjectives. He said, these people are telling me that when I don't look in my bedroom, the bed could be anywhere in the room. And when I open the door and look in it, it instantly goes to the last place I left it. And so how stupid can they be, right? I mean, this is Einstein giving us a description of how stupid he finds quantum mechanics. But I have written a book to show that all the really deep things in quantum mechanics that they were arguing about in 1927, and then in 33 when he talked to Rosenfeld, and then in 35 when he produced this paradox for them, which he's designed to show them how stupid they are. What is Einstein doing? Explain that one. That's what he's doing to them, putting a finger in their eye. When you read him what he's saying to Born, he's annoyed at this fundamental randomness. He doesn't like randomness. He's a determinist. But he's coming to accept a certain amount of randomness in quantum mechanics, so this is difficult to explain his mind. I've tried to read everything he says. I can understand when he's thinking what. But anyway, if he had called it knowledge at a distance and left it there, we'd never have quantum entanglement, I swear. On the other hand, quantum entanglement turns out to be a very useful tool. And why is it a useful tool? Because we can instantaneously, at faster than the speed of light, appear to have acted on Bob's particle by Alice. But it is only an appearance. These are not acting on one another. They are doing something that's coordinated perfectly by the law of conservation of angular momentum. So let me back it up to where you might be able to accept it. This law is at a deeper level than quantum physics, a deeper level than classical physics, because it underlies, and Hoffman likes foundational. This is fundamental below physics, that momentum will be conserved for symmetry reasons. Unless someone...
This is below physics? How is this below physics?
It's more fundamental. Well, it is physics. Conservation laws are physics. But it's more fundamental than laws of motion.
It's like more foundational.
More foundational, if you like.
Things
A word you've been helping him explain when he talks about it, right? You see him saying things like that? Consciousness is what's fundamental in conscious realism.
Sure.
So the question is, what's the most fundamental? A lot of people today talk about what are the fundamentals of reality below quantum mechanics. So I'm telling you a fundamental that I would like to stress, which is a conservation principle. So now let's imagine what's going on. The two particles are set up and they leave one another. Now, Bohm said they're atoms. So he said, let's start with a hydrogen molecule. And the molecule has two atoms connected together. And the reason they're connected is each one of them has an electron in its lowest shell, unless it's excited. So it's got principal quantum number 1 and angular momentum quantum number called by the letter S, 1s, 0, no angular momentum. And the other one is the same. But now we know that if it has a spin, the other one must have exactly the opposite spin. I'll try to go into how physics came to learn all of that. Because in the early days of Bohr, we thought, let's just look in there and find where the electron is relative to the nucleus, right? It's somewhere, right? It turns out every attempt to say it was somewhere, that it had an orbit, we still use orbits in all our atomic
It's
pictures.
not quite right, but
The point is, Heisenberg and Pauli and all came to the conclusion that it isn't anywhere until you measure it. Now, you can see that idea. Now, that's the idea that pisses Einstein off, really. Surely it is somewhere. It's a particle. It's got mass. It must, when it's going, take all its mass along with it. What do you mean it isn't anywhere? You mean it's everywhere? Schrödinger said, listen, it's a charged particle. And what's going on is that the wave function he's discovered is distributing the charge everywhere. So the correct way to think about an electron shell in chemistry is that it's just charge everywhere. But charge only comes in quanta. Charge is a thing which is quantized. It can't be all of those places. So what is our current thinking about a molecule or an atom? The thinking is that the electron is probabilistically found anywhere. It's as if it's moving, but it occupies all possible phase space cells, all possible positions, as many velocities as the energy allows it to be, and it does all of these. I'm approaching the level of truth, which I'm not getting there. Nobody thinks they know what an electron is actually doing. What we do know is that Schrödinger gave us an equation, and this equation, psi, you square it, you get a probability of finding the particle somewhere, you measure thousands of times, and your measurements agree perfectly with our predictions. What better science could we have than that? It is the most accurate and most firmly understood theory of all, but it boggles the mind. How can we be saying it's only probabilistically somewhere, and then when we measure, we find it distributed in the course of many experiences, in my mind, and experiments, to be distributed among all of those perfectly as predicted by Schrödinger. Okay, so Schrödinger, though, said maybe the electron is spread out everywhere. They called it smeared out. He had words in German and all. And Einstein thought that a light wave, remember Schrödinger is working in 1926, 27. In 1905, you know the story of the photoelectric effect experiment?
Yeah.
Okay, let me take you Einstein's thinking through the photoelectric effect. Well, we all know, he says, that light is a wave. And light, when it leaves a candle, it goes out in all directions, spherically. It could be found in any direction. Light is going everywhere. But when we look at this emission of an electron, kicking a light energy, kicking an electron and converting light energy into motion energy of the electron, it emerges from a single place on this electrical plate, which had to have been charged for this to happen. The photoelectric experiment is, there's a plate, you put a voltage on this side, positive, negative on this side, it's all charged up like in a vacuum tube, or also going on in a transistor today. We have a bias on the whole thing. You turn on the light, boom, electrons start popping out of the metal electrode. What's going on? I turn on the light and they come out one after another. Einstein's worried about that for probably 6 weeks when he came up with this unbelievable thought that maybe light is not a continuous wave, but it's a whole bunch of particles. One of them hits that plate and knocks out an electron. You are now holding on to the incredible discovery of almost everything important in quantum physics. There it is right now. Yeah. When I started reading this in Einstein, I thought, this is fantastic. Yeah. People told Schrödinger, Pauli, for example, told Einstein, who didn't like this explanation, told Born, who eventually became famous for the probabilities as what are called Born rule. He upset a lot of people with this description. Planck, who had found the Planck constant 5 years before Einstein used it to explain what's going on. It's an amazing time.
It is.
And there's a lot there. You can see there's a lot there because the layman is so far from understanding this, but you're coming along. It's a path I'm hoping to take people along in my reading and writing and putting it all up here. So we're on, Einstein is saying the light is nothing but a lot of individual particles. They're randomly distributed, and Einstein too knew that it was the square of Schrodinger's wave function that tells you where they are. But he didn't like it. He didn't like any of this. He didn't like the world. He said God, he wouldn't play dice. He didn't mean there was a God, but he did mean that a rational universe would just not be organized with this stupid randomness in it.
Right.
And he says a lot of nasty words about the people who think so.
All right, so if we could just put a pin on the,
Yeah,
because I
there's
do
a
want
lot
to talk about the book. I do want to talk about the famous expression that
The-
book.
which one? Yeah.
Oh, my God, he plays dice.
Maybe,
Well, you just-
no, not
maybe you wouldn't have to,
necessarily.
but
This is Hoffman on Crick, and it's his opening of reality. And this is him taking a position against Crick and against David Marr, who believes that vision is our best tool to getting to what's really going on in the world. And I think every scientist, mostly when they think of observing and measuring, they're thinking in terms of vision, the equivalent. We can extend our visual range into any wavelength, small, large, and we can see more and more of what's going on. There are limits when we get to the small. We're pushing limits when we get to the large. But Hoffman, I like him a lot, but I have a feeling he's totally off on the question of whether or not we're approaching truth or getting a better understanding or knowledge of the real world. Einstein wanted an objective world doing things according to rules that didn't involve randomness, so he was upset with the quantum physicists, but he figured out almost all the problems of quantum physics, which they then got famous for later. And that's what that book is about. So let me jump back to Hoffman. He had read Astonishing Hypothesis, wrote to Crick. So I don't see why you pick on neurons, Francis Crick wrote on April 13, 1994. Surely you believe the sun existed before there was anyone to perceive it, so why should neurons be different? Okay, neurons didn't come into existence until we had observers and conscious observers for them. A few weeks earlier, Crick had kindly sent me a signed copy of his new book. That's great, like talking to Chomsky. That's an experience. I wish I had more of that. So I read it and sent him a letter on March 22nd, 1994, thanking him for the book. I also raised a question about its hypothesis. Now this is him. Perhaps you could help me escape what seems a paradox. I agree wholeheartedly with you that, quote, seeing is an active, constructive process, end quote, that what we see, quote, is a symbolic interpretation of the world, quote, we're not yet to the level of truth, and that, quote, in fact, we have no direct knowledge of objects in the world, end quote. And now, end quote, back to Hoffman. Indeed, I think perception to be like science, a process of constructing theories given the available evidence. We see the theories we believe. As you say, seeing is believing. And I noticed when I wrote this, my old idea is, no, we'll see it when we believe it. Because that's when we have our vision, when we're locked into belief. And it's wonderful to watch Hoffman steer away from belief. I'm not ready to go to belief yet. Watch him, his words on that in your interview. By the way, I have your interview right here, and you can see I'm only a third of the way through, and I was thinking what today we could do is watch it together, and you and I could talk about what he's saying, and you could help explain him, and we could all get together on this. All right, but now, so on these points, Crick and I agreed, but they conflict with common sense. Now, where does he say it in here? He basically says he can now prove that that Crick has got it wrong, flaw in the theory. But then I set up my paradox. If we construct everything we see, and if we see neurons, then we construct neurons. But what we construct doesn't exist until we construct it. Coming from quantum physics and its strange ideas about when it does exist. But we didn't exist until we construct it, open paren, too bad, it would be much cheaper to move into my dream mansion before constructing it, end quote, whatever that is. So neurons don't exist until we construct them. And that's what's wrong with Crick. But that is what's wrong with Hoffman. Anyway, that's the paradox. It's very interesting, and I write here, very good. But this conclusion, I wrote in the March 22nd letter, contradicts, it would seem, your astonishing hypothesis, namely that neurons, that we're bundles of neurons, and they exist prior to and are somehow causally responsible for our perceptions. And I say that's absolutely, why did I write very good? The point is that the neurons are there, we get to do what my experience recorder and reproducer with them, and that's what it means when we remember having seen things, or having other experiences of getting burned, or all the things that go into being our knowledge and our life of the world come into us at one point in time and get recorded in neurons that have gotten wired together, including emotions, pleasure, feelings at that time, which goes to explain David Chalmers' so-called hard problem of consciousness. How can these feelings, the senses of which do not exist in the world, like red, wavelengths exist. Our sensory system turns it into a color. Colors don't exist. He starts off with a quote, was it him or, no, maybe it's David Marr. David Marr starts off with this quote, colors don't exist. And he correctly, I think, maybe I take it back, even in ancient times, the Greeks said, many things don't exist. They're all made out of particles, atoms they call them, right? Those are the only real, that's what you get when you get to the bottom of reality. Well, now with quantum physics, we get down to atoms, and they're not that so easy to imagine, even though the Greeks imagined them, Democritus and Empedocles, all these guys, they imagined them as little things that hook together in different forms, and then Plato said, oh, maybe they're all geometric forms, and now we jump forward to Hami's theory, whatever his name is.
Neymar Carney.
Yeah, so anyway, that's that. Now let's switch to entanglement,
Sure.
all right?
Yeah, entanglement.
Now, if you're going to try to record this, it's on the screen here. Is your camera going to get that?
What are you going to record?
I'm going to show you
sure.
a visualization of a hydrogen molecule
Okay.
separating, because that's what David Bohm says is a perfect entangled thing, okay?
Okay.
So take
Well,
some notes. We'll
I
get
can-
this again. I'll send you a way
Hydrogen-
of seeing this, and you can get it off the screen.
If you send me the link, I can just see
Yeah,
over-
absolutely. You're
over
really
Bob's.
good at getting things, and then
thank you.
you illustrate in your talk. So I'll send you to, let's go to,
Yeah,
just-
just, if
my
you send it to
hearing
me, or
aids
if
is falling
I
up.
can jot it down, I can find it, yeah.
Let's see what that ear keeping me hearing. Let's open a new page. Click on Information Philosopher. Find a drop down. You see them all: problems, knowledge. We want quantum. Then we want entanglement.
Okay.
Now there's a great deal to this story, which you can see how much you want to read it and work it into what you're doing. And this is not working, so I'll just take this out for the moment. I'll just whiz by this page, which is an attempt to describe the problem, that the square of the wave function expresses the probability. Einstein's then impossible event in the EPR is described here. He discovered what we call today non-locality and non-separability. These particles seem to be not inseparable. They share properties. And then this is something he wrote, anyway, too many details. Einstein described a situation to Leon Rosenfeld in 1933. He said to Rosenfeld, what do you think of this situation? Suppose two particles are set in motion toward each other with the same very large momentum, and they interact with each other for a very short time when they pass at known positions. Consider now an observer who gets hold of one of the particles far away from the region of interaction and measures its momentum. Then, from the conditions of the experiment, he should have said, because of conservation of linear momentum, history would have gone a totally different direction if he'd said that right then. But he didn't. we will obviously be able to deduce the momentum of the other particle. We will deduce the momentum. Same with position. We measure the position, it's symmetric. The other one is symmetrically on the other side of the original. Therefore, we know where it is. Yeah. If he'd said knowledge at a distance, Carlos, if he'd said knowledge at a distance, we would not be
having,
But here's the thing. Quantum entanglement is a useful tool today. It's the basis of quantum information theory. It's the basis of quantum encryption and a couple of other things which I can show why those still work in the world. We are able instantly to have bit strings of random up, down, up, down, up, down at Alice and Bob randomly in real time. We could spend the next 5 minutes and set up streams of bits in Alice and Bob, and these are perfectly used as ciphers, as codes, as one-time lookup code to encode. Alice can now encode a message, send it by regular channel to anybody, or particularly to Bob. Bob can then apply his to decode the same thing. And we in fact have instantaneous quantum communication, uninterruptible, nobody can eavesdrop on it. Because if when we eavesdrop, the bit strings change. There's a whole story to entanglement. People who, when they hear my explanation, they think I'm saying quantum entanglement isn't real. It is real, but it's only appearance of something going faster than light. So now we're recording, so before I go to the screen, let me just put it in words and then we'll look at the screen.
Yeah, sounds good.
Imagine then conservation of angular momentum says formed with, instead of position momentum, we're now going to angular. So the initial entangled particles, one is up, one is down. Now, they are never they never change from total spin 0 to total spin 2, or 1/2 and 1/2. They never change. That would violate conservation of angular momentum. They can change if someone touches them, one or the other. But they do not do that by themselves for reasons of time symmetry, no cause, no effect, no change. So they start off opposite to one another. But as quantum says, we don't know where they are exactly. We only know they're opposite. So now there's another kind of symmetry, which is to say it doesn't depend on the angle that they are. They just have to have total spin 0. And it's not like we know that they're at an angle and that they're spinning tops. The spinning tops is a world-level vision of things that spin. But spin is not, it's not that. It's not okay, but they're opposite to one another. So here comes my theory now. At all times from the time they're created, wherever they could be found, they will always be found opposite. Always. No matter which angle you measured because of the symmetry. Therefore, the reason these two are found to be exactly opposite, even though they are both randomly found, up or down, is because of the conservation of total angular momentum. It's because there's a cause coming from their original preparation, which stays true because we can't allow the total angular momentum to be other than 0. And it's true at all times, no matter what they're doing. Not that we know what they're doing, not that we know they're in any particular place or in any particular spin, but that they are always opposite to one another. That's my work. It's a big one to hang on to.
Show me the visual.
So I had created these diagrams that show what Einstein was talking about. Look, if that one went that far, then that one went that far, right? I mean, hey,
they've got it.
Why didn't he draw a picture? We would have been alone.
Saved us a lot of time,
We need some visuals. Okay, so then I go on and I talk about how it works. I talk about what Einstein said to Rosenfeld, and then this stuff is only paradoxical. Einstein says, how can the final state of the second one be influenced by a measurement performed on the first one? Whoop, he set us off in the wrong direction. This brilliant, most brilliant of minds in the scientific universe made a super incredible mistake. It looks as if I touch this one, I affect that one. He called it an influence. There's no influence. Not if they are both of them in a state such that if you measure one, you get the other one in the opposite direction. If you're with me now, you're going a long way just to be smiling now, because I have not succeeded in writing this up in a way that anybody has agreed with me yet.
Okay.
And you can stay, skeptical until we get further along. So why does Einstein describe it as an influence? And some suggesting what he later called an action at a distance. It's paradoxical because Copenhagen says they don't have a position. And I'm not saying they have a position either. I am saying that we don't know the position, we won't know it until we measure it, and so you could say it doesn't exist until we measure it. You could say our measurement brought it into existence. You could say that. But what you can't say is that they are different from one another when found, that they are in fact perfectly coordinated, perfectly correlated with one another whenever they're found, because there's this deeper, more fundamental principle that they must always have total spin zero, no matter what they're doing, because of the symmetry. Now I'm going to try to show you an illustration of that, and it'll be anyway, lots more talk about the same problem. This is going so far, I'm thinking, what do I have to say to convince people? And I'm writing all this stuff. Can they have specific properties determined before they are measured? No. But can they have perfectly correlated, yet indeterministic or random properties created by the measurements? I say yes, as long as Alice and Bob measure in exactly the same direction. Should one of them measure in a slightly different direction, they will influence one particle differently from the other one, and you will have changed the momentum of one to not be opposite. This is a little complicated.
Yeah.
But unless you preserve the symmetry, you'll get a result. If they're at right angles to one another, it turns out they're totally decorrelated. If Alice measures and then Bob measures at right angles, zero correlation. Both random still, but no correlation in the two streams. They must be on top of one another. Now, Bell knew that, and I'm surprised. I try to read Bell and say, don't you see what's going on? There's something else is driving this. And he talked about how it varies with angle. And his Bell tests are done with angles, different measures. And I'll show you one thing. I hope your camera's still running. Oh, no, I can't do it. Hey, Holly. The thing I want to show you is in my bedroom. Let's not do that.
That's okay.
So let's see. Let's go down here, and now I think I've turned off a few people to whom I've tried to describe this by saying, when you have a conserved property, sometimes in classical mechanics you call it a constant of the motion, that it's always true, this constant. So the total angular momentum being zero, so they must be opposite, that's a constant of the motion. Now, David Bohm said, maybe there are hidden variables. You've heard the phrase here. Maybe there are hidden variables which are able to signal somehow these variables can, when you measure this one, something goes to the other one and makes it match. Or that's how it would have to happen, right? If in Einstein's or in Bohm's version, you measure this one, you find it here. Well, the other one is, we don't know where it is, so it's anywhere. Something must now lock it into to be perfectly opposite. He goes along with this theory that there's an action, that there's a faster than light action. Many of these people who are into entanglement, they believe something's going faster than light, and we just don't understand that yet. That the universe is all connected instantaneously, way beyond the evidence. Okay, so I called it a hidden constant of the motion to go along with hidden variables. You don't need a variable traveling from here to there as long as something is always true. A condition is what's hidden. A condition that these two must, upon being found, they will be found opposite.
So how does Alice know? Okay, let's say so angular momentum has to be zero, right?
Yes.
Bob is out here and he's like this.
Right.
How does Alice know how to make it zero? Like Alice needs something
Listen,
to tell.
the two particles, when measured by Alice and Bob, are found to be opposite to one another.
Sure.
Okay.
Yeah.
It's not because anything Alice does sends information, this, when I try to analyze, to go to Bob, to get Bob organized, and to be, nothing happens like that. Instead, something is happening which is always true. It's always true that these two electron spins are opposite to one another, should they be measured. It's always true, not because anything is, I do it, but no, you understand, when Alice measures, she believes quantum mechanics that it doesn't have a value until she gives it one. I'm changing this. I'm saying it's true that it doesn't have a value it can have the one she measures. It will have the one she measures because she chooses to measure at angle 0. That's her free choice, it's called. She decides, and she creates momentum in the 0 direction. If Bob measures at 45 degrees, he's not going to get perfect agreement with her. But if he measures also at 0 degrees, because when she measures and gets up, the total is 0, so he gets down. Not because anything went between them, but because they are always opposite to one another in electron space, or in it's almost, electrons are beyond just thinking in terms of ordinary mechanics, because they aren't really spinning, they aren't little balls, or all of that. You're good. I can see your hesitancy is good. Because I haven't convinced
anybody. I just
anybody.
still can't.
Yeah, that's okay. Let me now show you.
Because I can't figure out. I can get behind you, of course, what you're saying with angular momentum being 0, having to be 0.
Okay.
And that's sort of like a fundamental thing. Okay. It's
exactly
more fundamental
than particular
so they have to,
orbits.
I can imagine them having to like sort of abide by this value.
Yeah, it's not like they're listening to the boss and abiding. They are just there because of laws of conservation and symmetry. But
so would you say that value of 0 is like outside of this system or something?
Below, maybe. I wouldn't say outside.
Yeah, below. And so
more fundamental was good.
Would you say they're communicating to that value in some way?
They're not communicating. This is important in my view of what information is and how it gets communicated. There's no communication between Alice and Bob once they separate.
Right. I know as much as I've read about quantum entanglement, as little as I know about it. As I do know that everyone agrees that you can't send information this way.
And yet some want to believe it. You understand that? Many of them are saying there's something going on that we don't understand yet about space and time.
Yeah.
There are at least some of them who want to believe in the superluminal world. Yeah.
But I have learned, like,
you're right,
minimally, that this couldn't be used as a way to send information.
That's perfect.
That I know. Perfect. I'm pretty sure about.
But it can be a way to have information appear at Alice and Bob over the course of a few minutes to develop a cipher. And that's quite amazing.
Right. Yeah, you can use it for that kind of stuff.
Either you see that the way I see it. It's two things happening because they have a common cause or condition. It's not a cause in the sense of a causal chain going down to Bob and another causal chain going down to Alice, where God or the laws of physics have given them this result. Many people like Bell and himself and Paul Davies, they say what's going on is superdeterminism. This all happened because of cause and effect, and the physical world is totally deterministic and causal. That doesn't work. I get the same result they do, but I don't say it had anything to do with determinism, because they are both random. And here we are accepting randomness at the same time we accept determinism of sort.
So is there a visual?
Yeah.
Because I mean, if this whole time you could have just shown me a picture and then
first of all, I have a long write about disentanglement, because Schrodinger talked about what could happen to disentangle them. So that's important, and most people don't ever write about that part of Schrodinger. So I've got that in there. Here's the equation, which this is David Bohm writing. And he says, we consider a molecule of total spin 0 consisting of 2 atoms, each of spin 1/2. The wave function is therefore psi, the wave function, is 1 over the square root of 2, square it to get 1/2 probability that you'll find plus minus. Minus, that's because they're what are called fermions instead of bosons, if you've heard those terms. When you exchange fermions, they cause the sign to change. When you exchange bosons, they don't change, and that's why this is minus. You can either get a plus minus, Alice Bob, up, down, or down, up, each with probably 1/2. And here it explains the whole thing. I think you've got all of that. But and this is Bohm talking. Then, because the total spin is still 0, it can immediately be concluded that the same component of the spin of the other particle is opposite to that of A. And I say, David, Bohm, why didn't you tell him that's because of conservation of momentum? It's obviously what he's using. Carlos, I have read Bell carefully, Bohm carefully, back to Einstein, of course, several other people who've commented in recent years. Only 2 people have mentioned conservation of angular momentum. One is a scientist in India who's got a bad reputation, and I mentioned him to one of my people citing him, and I cite him somewhere. They say, oh, he doesn't know what he's talking about. And one other one, I can't remember who it is. Anyway, sadly, here's John Bell, and I talk about what Bell is working on it, so there's a lot there. Bohm and Bell are implicitly using the conservation of total spin, supporting our hidden constant hypothesis. There's a condition today, I call it. And it's that condition they are always happening. Whenever they are seen, they must be opposite for reasons that are deeper than quantum mechanics saying we don't know what they're doing, and they could be doing anything, and so therefore they don't exist. In fact, when it's knowledge, information in the sense of knowledge, we don't know what they're doing, but do they not really exist? Hoffman would like to say, no, nothing exists, nothing until we are conscious of it. We need conscious observers. That's not the explanation. Okay, one more diagram, and I think this one maybe is a, whoops. Wow, look at that. See what that did?
Yeah.
Did I show you this?
You did.
Yeah, okay. But now we've lost our place. Let's go back down. I would love to have you understand how that works and why that could be done in other websites that attempt to archive everything they ever do so that you can tell when people changed it and who changed it and all that sort of stuff. So we got the wave function. Here's the experiment that Clauser, Horn, Shimoni, and Holt. So those four guys, Michael Horn, I met him and wrote to him, and he never answered back. He's a local university, was at Boston University, but also at Suffolk, I think. Anyway, he died. Abner Shimoni died before I could write to him. Michael Horn, I wrote to him, but he died. John Clauser, I've written to him, he doesn't answer me. He's got a Nobel Prize, and he doesn't have to talk to me. Richard Holt is alive, and he responded, and I'm still trying to get him working through the way I'm trying to think about it, and I can't say we've gotten anywhere. I can't say that he really understands what I'm talking about yet, but I'm working on all of them, because those are the guys who do the most famous experiment, or describe it. So then, we prepare information and then conserve it, is my explanation here. Here's another description of the wave function. Here's one where I tried, I think, to animate it. See, it's animating. Come on, Bob. Anyway, open image. Let's try this again. Anyway, this is a step through why if you measure one here and then Bob waits to measure, his result will still come out because of the conservation law. There it is animating. This is my attempts to get an explanation. Why do so few accounts of entanglement mention the conservation laws? I can't understand it, because this is so, it's really one of the great solid basic things about physics, and nobody wants to turn it on in this context and talk about it. So now, one more thing about the molecule before we go to the illustration. When I wrote my PhD thesis, I wrote about the hydrogen molecule. And the reason I wrote about it is because we were trying to puzzle over certain radiation that comes from stars nearby. We first saw with rockets going into space around a star called Spica. And it had lots of ultraviolet light between 1,500 and 2,000 angstroms or something like that. And I wrote this thesis in which I said, when the atoms on the surface of a star, in the sun's case, get close together, two hydrogen are colliding, it might be better to think of them as molecules, not atoms, and use molecular wave functions, not quantum wave functions, atomic wave functions. This is a little subtle, but I came to be an expert on molecules and their interaction with radiation. My thesis was on the continuous spectrum, because it is a very continuous, lots of different wavelengths of light of the hydrogen quasi-molecule, I called it. It's more treatable as a molecule because they're close together. Turns out this is exactly what everyone's talking about in entanglement. And every time I've been reading about entanglement through the years, I'm saying, I've been here before. I think I know something about this. And now I'm finally trying to write it down and connecting it to the molecule. So, and my quasi-molecule. People now use the term quasi-molecule, but when they search it, they find that it's in my paper, the first one. Anyway, visualizing it. And Feynman, wonderful guy, I talk about what he's doing. Here's another animation, my early one, to say, look, they were prepared in a singlet state with total spin 0. It's conserved. And they always are found in opposite directions from the source, conserving the total linear momentum. When one is measured, that's what I just told you. We know that. But I wanted more than this. I wanted an animation. And I thought, gee, I'm going to get these kids at Leslie University who are animators. I'll get them to help me design. Can I get to talk to kids? It turns out to be very complicated. But what I did find, I say, why did Einstein and Schrodinger both think there was an asymmetry here? Because there is a deep symmetry here, and it's the secret to why they do things in a conserved way. Because as long as, and that's what I'm talking about here in the EPR paradox. Now, there's this whole subject. You know that if Alice measures first, there is a frame in which, if you're traveling fast, coming from the B direction, special relativity tells you that B measures first to that observer. Now, I take a moment deeply now. This is the whole story of special relativity. You can imagine a spaceship coming in here. Alice and Bob actually measure at the same time. They have to agree on the exact photon pair to latch onto. And they run their clocks and they take measurements at agreed upon times and agreed upon directions to get these results. So because when they measure simultaneously, some observers will think they saw Alice measure, and it takes time of light before they notice Bob measuring. Imagine this with me. The camera's not going to get this.
No,
But now if another guy coming this way, he sees Bob measure first. So the fact of them measuring first tells you intellectually, beyond believing in limited velocity of light, that they can't influence one another. What they're doing, Carlos, is being done at the same time, and they're very far apart. There can be no way any influence. This is another way of looking at it.
Well, are you saying this is accurate or this is inaccurate? Sorry.
This is correct. Now maybe you don't have enough special relativity.
No, the frame actually reminds me quite a bit of have you ever seen, what's his name, Green, the astrophysicist?
No.
What's his first name?
Oh yeah, I know who you mean.
Brian Greene.
Brian Greene.
And he has this visualization of the block universe.
Oh yeah, block universes. He's into relativity.
And you're taking slices.
Right, and you see different sequences of results.
And so is this similar, or is this what you're talking about time-wise?
Absolutely.
In that
there is no absolute time for everybody. Clocks run at different speeds. Events happen out of order if they're in space separation. Two things that happen in a space-like separation, you cannot say, Einstein says, that there's an absolute time. I think even Einstein agrees, there is a cosmic time, which is the average of all times in the universe, so we can date the origin. So we come forward to today. It's today now, we make measurements. But it is in fact true that if you're traveling, like the railroad train that Einstein uses as an example coming into the station, you will see this thing at a different time than the other one. Rather than going there, I'd like to work on that.
Can you test this? I mean, can you make the slice, the angle? Is there a way to test if this is correct?
Well, this is sort of fact rather than. I'm not sure what you mean by test.
Well,
yes, we could.
But if you might, is your claim that when you measure A,
yes,
and then you measure B at some point later, let's say,
right,
anytime later,
or simultaneously,
a year later, or simultaneously.
The way it's done. Yeah. But what does simultaneity mean? Einstein says there isn't any simultaneity because I can make these two events happen one before the other, or either one. That's what he did to time. Why everyone thinks absolute time of Newton went away. It's this thinking right here, which most people, I've never seen this being presented except Roger Penrose. He has this diagram in his book on the something of reality. What's that title? Do you know the Penrose book? Big fat book, something like reality. Anyway,
okay.
Penrose called this the Andromeda paradox. If someone in Andromeda is preparing a war, going to send the generals out, it turns out it happens after the war is over. Penrose is doing something a little weird with it, but this is a very interesting way to think about what's going on and when it happens. Things that happen simultaneously can be seen as happening one before the other or the other before the one. And this is a part of understanding this entanglement. But let me move on. We'll come back to it. So I'm saying no hidden variables, but maybe there's a hidden constant. So now here I do one more animation. Now this time I try to show that as they move, they are always opposite. And it looks like this. See, they're always opposite? But as I go along, see, I can do this and make them travel, right? I thought I could grab a hold of this. Yeah, you see them moving? They're just always opposite.
So they're not in a superposition?
Now, in this case, this is one, you'll follow my explanation. This is the one everyone criticized me. This one suggests they had the measurement positions all the while. But I know you and I know that they're in lots of different directions, but they're always opposite. So I need another animation, something like this one now. And let's try this one. I'm showing them now as, if I go slowly through it, I'm showing them that they're always opposite, but they're in a random position. So in the time when anyone chooses to measure, they might get down up or they might get up down. Depending on what they're up to at the moment, moving together with a condition of conserving total spin 0, but not in any particular direction until it's measured. Now that's a big...
Yeah, I guess how do they maintain the connection until
There's
they're
no
measured?
connection between them. Just a condition.
But
no
this
connection.
visual there's what connect? What'd you say? Connection, not a.
Say again. This is trying to show what they're doing, not to suggest that either one knows what the other one is doing, except we can know what the other one is doing when we measure this one. It's knowledge at a distance again. There's no action involved between them.
But they do have knowledge of the other.
Well, if I measure this one, I will know something about the other, provided I maintain the symmetry and measure in exactly the same direction, Alice and Bob. All right, let me go to my final one, because now I'm a molecule guy, and just a few weeks ago, I said, maybe I could use 3D Studio Max, or maybe I could do Maya. Oh man, Maya, what a learning curve. Maybe I can do SolidWorks, which was what Carter does, and CAD-CAM, and I can show two blobs of probability separating. And then I said, wait a minute, why don't I just search for anyone who's ever animated a molecule, right? And maybe I could explain it. You're the first person who's seen what I've just done there, so let's go down to this one.
That's it.
Principal theory is a constructivist. This is the difference between a theory which is true on principle. It's true for deep reasons like symmetry. Einstein said the great theories are principles, not constructed from assessing the experiments that are leading us to believe something. A constructed theory is flawed because we constructed it. A principle theory, if we discover it, it's true because it's true. This kind of talks to Hoffman's truth. The principle of relativity. Einstein said, I've got a principle theory. And he cites some other ones in a wonderful article on the difference between a principle theory and one that we think we got from the data, from the experiment. Those are two different things.
Sure.
So I want to say, as Einstein should have said in his discussion, the conservation is a principle. Neither particle is influencing the motion of the other. One to keep their momentum perfectly opposite. Show me with Einstein again. Let's say we hit two particles. They take off. Is one influencing the other? Yet they're doing something which, when you measure this one, Einstein says the other one has been acted on or influenced at a distance. No, Einstein, no action, no influence, just the fact that the principle of conservation of momentum tells us, hey, I find this one x from the center, the other one must be minus x. That's all there is to it. It's like I'm not going to anything profoundly puzzling, how something's going on. There's nothing going on. It's just a condition of the states of these two required by a symmetry principle and a conservation law. And I think I thought people are going to love this if I talk to a really good physicist. I have so far. I'm striking out. They've already read this argument and they say, oh, I'm trying to make the case that they always had these values from the creation to the... No, I'm not. That's why I wrote that first one, which I say, this is what you think I'm saying. I'm not saying that.
I mean, if I may...
Yeah.
It's like if you had two marbles, right?
Yeah, okay.
That's
fine.
Well, just two balls, whatever.
All right, whatever.
And when they hit each other,
Yeah.
One has spin up, and one has the up, and one has down, right?
If there were marbles, that could be true.
Yeah, if there are marbles, that could be
Okay.
true, right? And they're rolling and they're whatever. They hit each other.
Yeah.
They fly off. Angular momentum. The spin up or spin down is going to be the same. It's going to be opposite each other,
Yes.
right?
Yes.
Just like you're saying. Is
Yes.
this not?
Just by conservation of
Does this not
angular
make
momentum.
sense? Or
Yes,
yeah.
it does.
So momentum's going to be the same, but also,
linear
but also, if you were to stop, if you were to stop one
Yes.
and stop the other at the same time and not look at where the arrow is pointing over
Yeah.
here. Look where those pointing over here. It's going to be opposite.
Exactly.
Yeah.
You're with that. You're comfortable with that now.
I'm comfortable with that.
Thank you.
But I think is that not?
Maybe I'm over-convincing you or something, but
Well, you might
that's
be. I have to
that's
look
all
into
I'm
it
saying.
more. But I think what you mean, yeah, the problem with the hang up before. Well, the last analogy you made brought it together for me. When I started thinking of like superpositions,
Yeah.
that's where it gets complicated because
It could be
until it's
random.
measured, it could be there's a randomness.
What's the randomness got to do with it? Right.
Right. What's the randomness got to do? It's sort of like, oh wait, it's not at any one point.
Until
Before I
you
look
measure.
at it,
Yeah.
it's in a bunch of positions.
That's what
so-
led Einstein to saying quantum mechanics tells me I'm giving it its value, and in a sense I am, because I chose which direction to go in. But now the other one has to assume the opposite value, and it must have been an influence to do that. That's totally wrong. I've got my little book called Einstein Mistakes. They don't even write this one in there, but this to me is the one really big one that he hurt us by failing to appreciate a symmetry and a principle, a conservation principle that he knows as well as anybody in the world ever knew. And yet he said, I think it started with him saying, quantum mechanics says there's an influence, or I don't know how he got off on such a wrong foot. But it was in the context of his arguing with people he thought introduced a randomness he did not like. He called it a weakness in the theory, this idea that things happen at random. And yet he had shown, when he wrote this article and said, there is randomness in quantum, between when a light, remember his theory that the wave is not going off as a wave, it's going off as lots of particles? He showed, and I did the math in my thesis, and then more recently, where he shows that unless each time one of those particles goes off, it goes off in a completely random direction, so that over time it averages out to being spherically symmetric. Einstein's talking about a directed property which will, on the average, look undirected and be going on. He's saying, unless they're random, we can't get the same results as physics in what are called the A and B coefficients of the probabilities for emitting and absorbing, and then for what's called stimulated emission, which led to the laser. The stimulated emission, you can control that and have it keep coming out in the same direction. But Einstein talked about this fact that when a light leaves an atom, when an electron jumps from this orbit to that orbit, and a particle goes off, it must be that it's random. And what he called, not spherically symmetric, his term is, in German anyway, he said, this is hard to take. It's a weakness in the theory that there should be randomness involved in physics. 1905. It's 1927 before Heisenberg finally teaches Eddington that there's indeterminism in physics. So Einstein was a determinist, and when he discovered this thing, as I write it up on the Einstein page, it was a break in the world. Just 5 years earlier, Planck had accepted the idea that a light might, or energy might come in particles. Planck's constant tells you how much and so forth. Very exciting time. So I've read about Planck and all his worries about trying to prove that something's absolute, and back to the 1860s.